Hello and welcome back to part 2 of chapter 14. So in our previous video we were calculating r as r equaling 1 over n times the sum of zx zy, where zx is x sub I minus x bar over the standard deviation of x, and z of y is yi minus y bar over the standard deviation of y. So here's an illustrated example of calculating the correlation coefficient. So here we have USA, and then we have our x being 1300, our y being 20. So in order to figure this out, we have to get our y bar, which is if you sum up all of the x points, divide by the total number, you get 6,640 divided by 11, and you get your x bar equaling 603.6364. Same thing for the y. I sum up all the y points, divide by the total number, get your y bar. And then standard deviation is the same way we've always done standard deviation. You take your x group minus your x bar, and that's where you do your x minus x bar, square it, sum the squares, divide by n minus 1 degrees of freedom, take the square root, and you'll get your standard deviation for both groups. To get your z of x, you take your x sub I, so that would be like, so this, for example, the answer is 1.840. So that in order to get that, I'm going to write over here, we're going to use this formula. So you take 1300 minus your x bar, which is 603.6364, and you're going to divide it by the standard deviation of x, which is 378.4514. When you do this, this is what equals your 1.840. So that's all they did here, is they're just showing you that from this value over is your z of x. Same thing here when you do your y, use the same formula. You're going to do your 20 minus your 20.55454, we'll say, and divided by your standard deviation of 11.725, and that's going to equal your negative 0.047. So now when you have your values here of zx, zy, and that's this list and this list respectively, to get your zx times your zy, you multiply each data point times its data point. So you take your z of x for data point USA and z of y for your data point there, and multiply it, and that's where you get this value all the way over here. Then what you do is you sum it, right? That's what sigma means. So then you sum them all. So you add these all up, and that's where you get your 7.374. So then you go down here to the bottom, you'll see your equation where your r equals 1 over n minus 1 times the sum of zx, zy. So it's 1 over 11 minus 1 times your 7.374. Remember, that's from over here. And when you multiply that out, you're multiplying this by 1/10. You get 0.737, which would say that there's a strong correlation. So you'd say r equals 0.737, which there is a strong correlation there. When you do an SPS output, this is what it would come up with, and it's showing you that if you take cigarette consumption per capita and to the lung cancer mortality per 100,000, you get 0.737. Same thing here. This is cigarette consumption per capita times lung mortality, which is here. Now, if you think about it, this is your kind of like a 2x2 table here. When you have cigarettes consumption per capita and cigarette consumption per capita, it's the same number, so you should get an R value of 1. A very strong correlation because everything correlates to itself exactly. But you get 0.737. So when we're interpreting R here, we want to look at direction. The sign of R indicates the direction of the association. A positive R, it's either going to be positive, negative, or no association, which would be an R of 0. Remember, we'll go through this in a second. So the closer R is to 1 or negative 1, the stronger the association. The coefficient of the determinant is the square of the correlation coefficient. This is R squared. That's called the coefficient of determination. the statistic quantifies the portion of the variance in y mathematically explained by x. So for example, if you had an r of 0.737, that is what we just got there, and you square it, you literally just take 7.37, square it, your r squared is now 0.54. Therefore, we're saying that there's 54% of the variance in y is explained by x. Continuing on, reversible relationship with correlation. It does not matter whether the variable x or y is specified as the explanatory variable. Calculations come out the same way. This will not be true for regression. Remember I said you either have a positive or negative association, but the association is still there. Whether you have a negative correlation or a -1 or a +1, it's a super strong correlation to each other. Outliers. Outliers can have a profound effect on R. This figure has an R value of 8.2 that is fully accounted for by the single outlier. So here, if you see, all the data points are kind of like straight in a line, and you have this one outlier over here, and this gives you an R value of 0.082, which is a really strong R value. As you can see, that's really probably not the true representation of this. It's only because of this one big outlier over here that this is actually possible. So be wary of outliers. 6, linear relations only. Correlation applies to only linear relationships. So linear relationships being a straight line, we don't deal with arcs or any kind of curves. We really want straight lines. That's what the linear relationship implies. If there isn't linear, then there's no relationship. We can't say there's a relationship here. Correlation does not necessarily mean causation, so beware of lurking variables. Once again, just because you have a correlation doesn't mean it's 100% always. It's because of these two, this dependent variable and this independent variable that this happens. It's not always true. Sometimes there could be other factors in there, so you just want to always be wary and looking around for these lurking variables. A near perfect correlation, R equals -0.987, was seen between cholera mortality and elevation above sea level during the 19th century epidemic. We know that cholera is transmitted by water, not by miasma or elevation. The observed relationship between cholera and elevation was confounded by the lurking variable proximity to polluted water. So here's your -0.98 R value of the water source, and as you can see, as the elevation increased and the cholera mortality increased, you had this near perfect negative R value. But we know that's not true. We know that cholera is from bad water and not by elevation. I guess one way you could potentially look at it is that as you go higher up, water flows down, right? So potentially there could be the reason why. Remember that remember in the very beginning of the year, John Snow, in our slides, the father of epidemiology, was the one who discovered that contaminated water was the cause of cholera. So here we have hypothesis test, and when we do hypothesis testing, you have randomly select from a random scatter can result in apparent correlation, right? So if you just randomly select these data points here, you can see that there might be a thing. So we conduct hypothesis tests to guard against identifying too many random correlations. So how do we set up a hypothesis test? Well, we let rho, this symbol here is rho, not p. Don't confuse it with p. I know it looks similar when we type it out, but it's not p, it's a Greek letter. So let rho represent the population correlation coefficient, where we have our null hypothesis where rho equals 0, versus our alternative hypothesis where rho is not equal to 0, rho is going to be greater than 0 or less than 0 for right-sided, left-sided. Our test statistics, our t-stat, is going to be r over the standard error of r, where standard error of r is going to be equal to the square root of 1 minus r squared divided by n minus 2. Remember, n minus 2 will be our degrees of freedom. We're going to have two different points we're looking at here, so n minus 2. We're going to convert the t-stat to a p-value, so this is where we're going to use our t-stat table again, which I believe is table C in the back of our book, so that's where we go to convert our t-stat to a p-value. Remember that the table itself expands infinitely. I'm not going to probably be able to find an exact value, but we'll be able to approximate where it's between or greater than or less than. So hypothesis test illustrated example. So here we have rho equals 0. Remember, this is rho equals 0 versus alternative hypothesis rho does not equal 0, so it's a two-sided hypothesis test. We're going to get our standard error of r, so 1 minus 0.737 squared, remember that was our r value squared, divided by 11 minus 2. For our degrees of freedom, we had 11 data points in 2 sets, which is going to equal a value of 0.2253. So our t-stat is 0.737 divided by 0.2253 equals 3.27 with the degrees of freedom 9. You go to the back of the book, you'll see that our value is going to be between 0.005, going to be greater than 0.005 but less than 0.01 by table C. True p-value will equal 0.0097 by computer. Evidence against the null hypothesis is highly significant. Confidence interval for rho, we're not going to go into this. You're not going to need to know this, just still know what confidence intervals tell us. Confidence intervals are going to tell us, that the true value of the mean hypothesis, of the mean value is going to lie between the confidence intervals. This is the formula for it, but once again, I really want to just concentrate on R and the R squared and with our hypothesis testing, and then the little bit of regression we have. Okay, so I'm going to stop the video here after confidence interval. This is the formula, but you don't have to memorize this, just know what confidence intervals are and what they mean, and then I'm going to pick the next video up on regression, and we're not going to know everything about regression, but